Hello and welcome to eTech Video Production. Now if you have searched or somehow found this video, I know you are having a nightmare or losing sleep over EIGRP metric calculation. I hope after watching this video you get back your sanity. So let's jump right on it. And that metric calculation is this complex formula here. To behave like link state routing protocol, EIGRP use variables such as bandwidth, load, delay, and reliability. But those variables can be activated or deactivated with the K-value, and I have a table here so we can go over them. First on the table is K1, represent the bandwidth, and EIGRP will use the lowest bandwidth along all links. Here's a quick example. Router 1 is connecting to router 2, connecting to router 3. The link between router 1 and 2 is 10 gigabit per second, and the link between router 2 and 3 is 1 gigabit per second. The metric will only use 1 gig per second. Next is K2, which is the worst load on that link, followed by K3, which is the delay. In the delay is the sum of all delays. The link between router 1 and router 2 is 10 microsecond, where the link between router 2 and router 3 is 30 microsecond. The sum is now 40 microsecond. Next on the list is K4, which is the reliability and is the worst reliability of a link. K5 represents the MTU of a link, which is the smallest MTU of each link. And last on the table is extended attributes, which is used for scaling for bandwidth above 10 gigabit per second. K6 only in use when we use name mode EIGRP, so for our lab, K6 is not in play. So where does EIGRP get these attributes from? It is actually on the interface itself. I have a capture here on router 1 on gigabit 03, so let's take a look at them. Here is the bandwidth of 1 gigabit per second or 10 to the 6, followed by the delay of 10 microsecond. The reliability here displays 255 over 255, which is 100% reliable, where the transmission load and the receiving load is 1 over 255, which represents 0, and finally the MTU at 1500 bytes. Let's clean this up so we can continue with the default value. By default, the EIGRP on Cisco device have K1 and K3 as 1, where everything else is 0. So let's go back to this calculation to see which one is actually in use. K1 is 1, so this is in use. K2 is 0, and any number divided by 0 is considered undefined. Therefore, this is not in play. K3 is equal to 1, so the delay is in use. And K4 and K5 are 0, therefore they are not in use. So now the formula actually looks like this. The final metric calculation have 256 times 10 to the 7 or 10 gig divided by minimum bandwidth plus the sum of all delay. To be able to use load or reliability, you have to turn these K-value on. And remember, if you turn on a K-value of an interface, your other neighbor also must match that K-value as well. Many people ask me if they want to turn on this MTU or K5, where is the MTU actually fit in? If you look at the original formula here, MTU is actually not in there. So I have no idea how to implement MTU. Over the year, I heard one person said the MTU are used when you have load balancing and you want to vary the MTU. Again, there is no place for you to fit that. 1500 by MTU in this formula. I think whoever invented this metric calculation here drank one too many of those glass with a worm inside during their development. Now we have our final metric calculation. Let's head on over to our lab and perform a few metric calculation. Me personally, I think whoever developed this metric calculation here, and during their development they drank one too many glass that had that little white worm inside. Anyway, back to the metric calculation here. Now we have a simplified version of the EIGRP metrics. Let's head on over to our topology so we can perform a few metric calculation. My ultimate goal in this metric calculation is to figure out from router 0 what is the total cost to get to this remote network. So we have to begin with router 1 and what is the cost for it to get to the LAN. Since this is a gigabit interface, so that is 10 to the 6 as the minimum bandwidth. Followed by, we need to get the sum of all delay, and since this is the only interface, we'll find out what is that interface delay is. I'm here in router 1, so show interface gigabit 03, and you can see here the delay is 10 microseconds, so let's put that into our formula. We have a 10 here, so let's rewrite this, equal to 256 multiplied by 10 to the 7 divided by 10 to the 6, which is 10, plus n divided by 10, which is 1. So 256 multiplied by 11, which is equal to 2816. Let's log back into router 1 to see if that number is true. So with the command show IP EIGRP topology, highlight here is the output for 192.168.1.0 is directly connected on my gigabit 03, and my cost or the feasible distance is 2816 as we just calculated. Now router 1 will advertise to router 0. I have a way to get to 192.168.1.0 and my cost is 2816. Now all router 0 need to do is figure out his interface cost and add it to that 2816. So let's write this and calculate the cost from router 0 to router 1 for that network. Again, router 1 is advertised a cost of 2816. Since both interfaces are in gigabit, so this is no longer in play. And the delay is the same as gigabit 03 on router 1, so that is a value of 1. So 256 multiplied by 1 is equal to 256. So router 0 will add 256 to that total cost. So the final number should be 3072. So let's log into router 0 to verify that number. Here in router 0, show IP EIGRP topology. The highlight is the output from router 0 for 192.168.1.0, where it had one successor and the feasible distance is 3072 via 10.006, which is router 1. The number in the back is the advertised distance from router 1, where the number in front is the feasible distance. Let's take a look at more detail about this network in the topology table. And the command is show IP EIGRP topology for 192.168.1.0. First, the topology is for autonomous system number 10 for the 192.168.1.0. The state for this network is passive, one successor. The feasible distance is 3072. I have learned that from 10.00.6, and here is all my vector metrics. And the router that sent me that information is router ID is here. Now you can see the calculation for the metric for EIGRP is not too shabby. Now let's head on over to the topology table where we take a look at detail how router 0 built its entire topology table. Here I will be focused on router 0 and the 192.168.1.0 and 3.0. First, let's focus on 192.168.1.0/24, and router 0 learned that from router 1 at 10.0.0.6. First, the advertised distance. Router 1 will advertise 2816 to router 0. Router 0 will take this 256 and add to that 2816, and the feasible distance is 3072. Router 2 also advertised to router 0, so we have 10.0.0.10, composite matrix of. Starting from router 1 will advertise to router 3. He have a cost of 2816. Router 3 will take this 256 and add to that and advertise as 3072 to router 2. Router 2 then take this 256 and add to that 3072. Then finally advertise to router 0. My total cost is 3328. So that number goes here. Router 0 will then add this 256 to that number, and the final number is 3584. Let's redo that with the network of 192.168.3.0/24, and it also learned that network from 10.0.0.6, which is router 1, and 10.0.0.10, which is router 2. Let's clear this up. For the 192.168.3.0, router 3 will advertise both to router 1 and router 2. His cost is 2816. Router 1 will then take this 256, add to that 2816, and advertise to router 0 at 3072. Same thing for router 2. He'll take his 256, add to that number, and the number is 3072. So the number back here is 3072. Router 0 will then take the 256 here and add to the advertise of router 1, and the number is 3328. Same thing from router 2. Router 0 take 256, add to this advertised distance, and the number is 3328. Next, router 0 will find which is the fastest way to get to the remote networks. With the 1.0, this is its lowest number, so this is the feasible distance, and that network will be copied to the routing table. For the 3.0 network, both costs is the same, therefore both of them are feasible distance. Now router 0 have two successor, and both of these paths will be copied to routing table. Now, what about this path? Could that be our feasible successor or a backup route? But not so fast. For a path to become a feasible successor, there is a condition. And the condition is the advertised distance for that path must be less than the feasible distance of the best path. Let's re-examine this path. The advertised distance of this path, which is this number here, it must be less than the feasible distance, which is this number. In our example here, it is not. Due to afraid of this path can cause a loop in the remote network, EIGRP will completely remove this path from its topology table. Therefore, this path is not qualified as a feasible successor or a backup path for this network. In this particular example, we don't have a feasible successor, but on our next video segment on the advanced EIGRP, there will be feasible successor there. So you can check that out on the advanced video segment of EIGRP. Let's verify the topology table on router 0. We'll start by look at the topology table of router 0. Here is 192.168.3.0. The feasible distance is 3328. Both paths have the feasible distance of 3328. Therefore, I have two successors. Now let's take a look at 192.168.1.0. It only has one successor, 3072 via 10.6, which is router 1 out of gigabit 01. Let's take a look at the detail for show IP EIGRP topology for 192.168.1.0. One successor with a feasible distance of 3072. Now let's take a look at the 3.0. Two successor, 1 to 10.006 and 1 to 10.0010. And finally, let's take a look at the routing table. For the 1.0, only one path with a cost of 3072. And for 192.168.3.0, I am load balancing since they both have the same feasible distance. And that is how EIGRP builds its routing table. I hope this video has been informative. If you like this video, please click the like button below and subscribe to our video channel for more videos like this. Also leave a suggestion on other video technologies you'd like to see. Till then, stay safe as I will see you in another segment of eTech Video Production.